Okay, so let's look at some differential equations, and basically what you have to familiarize yourself with is that we can classify differential equations according to types and according to order, and then we can also classify them according to linearity. So that's three ways we can classify our differential equations. For the types, we technically have ordinary differential equations, and we also have partial differential equations. That's two ways you can classify them. And for the order, you have the first order, the second order, and stuff like that. And for the linearity, it's if you can express your differential equation in let's say maybe it's first order and it's linear. If it's first order and it's linear, you're technically gonna have some x function with respect to some x function multiplied by y prime plus some x function multiplied by y plus some x function. Let's just call it h at x. This will just technically give us 0. So from this one we can tell that it's linear because we have every x function. Technically it's just the y function. It shouldn't the differential equation here is not supposed to have a y function here. And you can tell that this is y to the power of 1. Immediately once you start to have y prime square, then already you can tell that it's nonlinear. It's nonlinear. So the order is this way. This is a first order linear equation. And if you have a second order linear equation, you can add some function k at x there. And then you have y double prime. And that's the second order linear equation. You can repeat the process and get the third order linear differential equation. And then you have some x function, let's call it m at x. And then you have y triple prime there. This is the third derivative of that. Then the process just technically repeats the same. You can do that for nth order for the differential equation. So we can either have a linear or nonlinear equation, nonlinear differential equation. So this is how we'll classify our differential equation. Notice that we don't technically stop at the first order, second order, third order. You can have multiple order of that. And then let's just take a look at this one. We have y double prime equals minus 25 over y cubed. Is this linear or nonlinear? Let's take a look at this one. Is this differential equation linear or nonlinear? Notice that if you can't identify that it's linear or nonlinear, just first rewrite it in the form of a polynomial and check what's happening. So by definition, if you multiply both sides by y cubed, then we have y cubed y double prime equals minus 25. And rewrite in standard form, then you have y cubed y double prime plus 25 equals 0. Notice that by definition for linearity, since we are in order 2, that means we technically have this one. But instead of having a function of x, notice that you have a function of y. So that technically makes this nonlinear. So it's a nonlinear differential equation. Okay, so that means you shouldn't have a y term multiplied with that differential equation. And also you shouldn't have this. You shouldn't square that, because immediately when you square that, you no longer have that linearity. You're breaking that linearity. And then let's look at this one. If we have y prime equals y over x minus 1, is this linear or nonlinear? You can use the same definition, but then you realize that you just have y prime and then you have x minus 1, y prime minus y. It's technically going to be equals to 0, and then we can identify that this is indeed linear. This is a first order linear equation, linear differential equation. And then notice that what about by order? We have discussed linear. So for linearity, you should have something like this. And if you can correspond that to that, then that means that the equation is linear. Let's give another example. Let's say y prime equals cosine x plus y. Is this linear or nonlinear? So if you check here, you have cosine, and then you have x plus y. You have a trig function. So if you realize this one, realize that you can, you have a y term here. What you can do is break it down and say divide everything by cos x plus y, and then you have something like this: y prime equals 1. And then notice that you have 1 over cos is secant, so you technically have secant x plus y, y prime minus 1 is equals to 0. This is a function that contains y, but by definition we shouldn't contain y. It should just be a function of x. So technically, if you have y or your independent variable inside a trig function, that already tells you that it's nonlinear. So it's nonlinear. because you have a y function in this. But you can technically identify this from the go. If you have an independent variable inside that trig function and your differential equation doesn't tend to simplify, then yeah, then that will be nonlinear. So that's all about classifications according to linearity. And what about by order? By order, you technically take the largest degree of the differential equation. So this y prime plus y minus x equals 0. This is a first order differential equation. How did I identify that? We just have y prime. The largest one in that case, just y prime. And this is just y0 in that case. So it's just a function itself. And then if you have y double prime plus 2y squared minus 3x squared equals 0 or some sort of that, then this is a second order differential equation. This is second order differential equation because technically you can see that the largest degree here is just to the power of 2. It's a second differential equation. And then if you have y cubed minus y double prime plus y prime equals 6x squared minus y, and what order is this? This does not represent the order, by the way. So then your order is technically, this is still a second order differential equation. If you look at it, it's still a second order differential equation. And then if you have y double prime cubed minus 6xy y prime equals 0, what order is this? Notice that the highest order in this case is this one here, y double prime. So this one is still a second order differential equation. Don't confuse this with this one. And then let's say we have this one here. We have y, and then we have something like this, and then we have y double prime, and then plus 6x. This will be equals to 0. What is the order of this differential equation? Notice that it can't be the second. This notation here, this y to the n, this is an nth order differential equation. It's not to the power. Don't confuse this with y to the n. This and this are not the same thing. So you have an nth order. In this case, it's just a third order. But in here, you have a second order. Which one is larger between the two? Is 3. So this one will technically be a third order differential equation. This technically will be the third order differential equation. So that's just our classification according to order. And then what about types of differential equations? So for the types, you technically have a partial differential equation, and then you also have ordinary differential equation. So you have partial differential equation and you also have ordinary differential equation. What's the difference between the two? Notice that here, for the ordinary differential equation, we technically write our derivatives in this form. Maybe x is a function of time, and then we find dx over dt. And that will give us some function there. And then for the partial ones, you're technically going to have something like this, where x is some function of two variables, and then you take this with respect to time. So x here is a function of one variable. It's a function of one variable. And for to take the partial derivative, we'll assume that x here is a function of two or more variables. And that will take the partial derivatives. So in an ordinary differential equation, you only have one independent variable, and you correspond that with one or more dependent variable. Okay, so let me restart that. This is the dependent value, and this is the independent variable. So here, this value depends on two or more variables. This value depends on two or more variables, but for an ordinary differential equation, this will depend on only one variable. But for partial, let's see. Let me just give an example. Let's say x equals st plus 5t squared. Notice that also s is some function of time. Suppose that s is also some function of time. Notice that x will now depend on these two values. X will depend on s, and it will also depend on t. And then that means that x is a function of two variables in this case. So you can only take a partial derivative of that with respect to maybe s, and that's just going to be the case in that case. So for an ordinary differential equation, we only need our x to just rely on one variable. Suppose that maybe it depends on t. X is the dependent variable, and it depends on t. only. It only depends on t. So that's how we will classify the differential equation. So let's see, dy dx plus dx dt is equals to okay, let me think of another example. Okay, let's say maybe that dx dt is equals to dy dt multiplied by 16. Is this an ordinary or partial differential equation? Let's look at it. Suppose that we are looking at our function x here. And from this order, it just says that x depends on t. If we look at this side of the equation, that says that x depends on t. But if you look at this other side of the equation, it says that y depends on t. And if y depends on, if y depends on t, what does that imply? It means that both x and y rely on t. Both x and y depend on t. They technically both depend on t. So now our problem here is that we have two independent variables, and if you check, a differential equation has to rely on only one dependent variable. So now when you have two independent variables, you're relating two functions now, so it's not gonna be an ordinary differential equation. So that will technically be a partial differential equation. But now let's say we have dy dt, let's say dy dx plus dx dt. This will be equals to, maybe let's say, it doesn't really matter what it's equals to. Let's say maybe it's some constant 5. So, or it can be in, I don't know, like an x and y function or a t function, stuff like that. So notice here that here you have y depending on x. So you have y depending on x. And here we see that x depends on y. Wait, let's check this. Y depends on x and x depends on t. If we look at here, we see that x depends on t. If y depends on x and x depends on t, that means we can rewrite this there in front. X depends on t. That means that y depends on t. So this is just going to be an ordinary differential equation. We have only one independent variable, which is y, and the independent variable is t. In the overall, if you look at the overall of this, you have y depending on x and x depending on t. So that means y depends on t. So that means you can technically say we're relating y and t. So that's just going to be that. So that's how you classify between ordinary and partial differential equation. From here, we can maybe say that we had dy dx being equals to maybe let's say 5xy, let's say 5 minus x, and then we have dx dt, that was going to be something about let's say positive x, and then when you add them together, then they just give you that 5. Okay, so that's the classification of differential equations according to type, order, and linearity.